Hello students and welcome to section 2 of our chapter Gravitation. In this section we're going to be learning about Newton's law of gravitation. Before we start with our topics for this section, we just take a quick check on what we've learned in the previous video. First one was simple concepts of gravitation. The second was circular motion and centripetal force. We all saw that centripetal force acts on an object that is in a circular motion, and this force on an object is directed towards the center of the circle and is called centripetal force. Some of the examples were moon, which travels in a definite orbit around the earth, and some other examples are the planets in our own solar system revolving around the sun. Now then we've moved on to Kepler's law, and here are those three Kepler's laws. The number one law is the orbit of a planet is an ellipse with the sun at one of the foci. Law number two is the line joining the planet and the sun sweeps equal areas in equal intervals of time. And law number three is the square of its period of revolution around the sun. In law number three, here we are talking about the square of its period of revolution of any planet that revolves around the sun, that is directly proportional to the cube of the mean distance of the same planet from the sun. Now back to our topic for this particular section is Newton's law of gravitation. Now the law number three from Kepler's law is the one that is the most important, which we are going to use in order to understand Newton's law of gravitation. So now Newton states that every object in the universe attracts every other object with a definite force. That means if let's say I have two balls in the same room, they both have some masses. We know because whenever we pick up any kind of ball, we feel the weight on our hands. So every object in the universe attracts every other object with a definite force. Now what is very important here is that the force might not be visible to us in terms of motion. That means if two balls are kept in a room and they seem to be stationary to our naked eyes, that does not mean that there is not a force acting upon them. So this is the first crucial concept that we all need to understand, that two masses attract each other, but it is not necessary that the force can be seen to the naked eye or seen by the naked eye. Now, going in deeper, the force is directly proportional to the product of the masses of two objects and is inversely proportional to the square of the distance between them. As usual, this is a word statement and we are going to decipher this step by step. So, the presentation of this law states that the force is directly proportional to the product of the masses. So, let's start here. So here I have ball number 1 and here I have ball number 2. Now there is a very clear force that is attracting them towards each other. So the law says that the force is directly proportional to the masses. So this is mass 1, this is mass 2. That means the statement has clearly said that force is directly proportional to the product of masses, which is m1 into m2. Now moving on to our next statement, and is inversely proportional to the square of the distance between them. Now as we can see that both these balls are kept at a certain distance. So this distance, I'm going to call this distance as d. You can call it capital D, small d, it does not matter. What matters is that this represents the mean distance between the two balls. So now the statement again says that F is directly proportional to the inverse, means 1 upon mean distance is d and the square of this value. So these are the two important statements that the Newton's law of gravitation states. So when I try to combine these, that means I can say F is directly proportional to m1 into m2 into 1 divided by r, or rather d square in our case. So this can be said as F is directly proportional to m1 into m2 divided by d square. And as you might have learned in your previous classes, whenever we replace a proportional sign with an equal to sign, there is a constant involved. So here I am I have a new constant which is g into m1 m2 complete divided by d square. So this is my formula for the Newton's law of gravitation. Now, some things about g. G is the constant of proportionality and it is called the universal constant of gravitation. Now, the universal constant of gravitation word or these three words are quite important. The reason they are called so is because the value of g, capital G rather, remember you need to make sure that you call it capital G because you're going to understand why capital G needs to be called it as we are calling it right now. Now capital capital G does not change from place to place in the complete universe. That means if I am on the sun and any one of you is on the earth, the value for capital G for either one of us will not change. Now, our solar system is quite small. If we move to other galaxies, the value of capital G still remains constant. If somebody is wondering what is galaxy mean, you can look it up on Google. A galaxy means our solar system is a very small part of our Milky Way galaxy. Similarly, there are many number of galaxies and capital G is constant in every part of the universe. Now the capital G has some value assigned to it. Now how we assign that value is what we are going to see now. So we know that F is equals to capital G m1 m2 divided by d square. So in order to find the value of capital G, what we are going to do is, or what scientists have rather done, they have chosen ideal values. That means they have assumed that there is a ball here and there is another ball here, or you can rather say an object. It does not matter if it is a ball. The only thing that matters is both the objects have some kind of mass. And this is 1 kg. This is 1 kg. And the distance, or rather the mean distance between these two objects is 1 meter. So what the scientists did, that the scientists measured the force that was being applied between these two objects. Now this force ideally was the gravitational force. Now the other thing that is important, that these two objects are 1 meter apart. The reason we are choosing 1 kg values is because the value that we need for capital G and capital F will come out to the values that will come out for these particular terms are going to be much simpler. That is why we chose 1 kg values, because they are easy for calculations. Now, once this particular experiment was performed, the value for capital G comes out as 6.67 into 10 to the power minus 11. Now, there is some SI unit that is involved here. So, we are going to see how this SI unit is going to be assigned. As we know that the SI unit for force is Newton. Let's do it in a much simpler way. I'll write term here and I'll assign SI unit here. So this is force. The SI unit for force is Newton. This is m1. SI unit for mass is kgs. So this becomes kg. There's another mass involved, so that is again kg. And there is distance involved, so that the SI unit for distance is meter. So all these SI units are going to come into play. So now we have to find the SI unit for capital G. We know that F is equals to capital G m1 m2 divided by d square. Now what I'm going to do is, instead of writing F, I'm going to write the SI unit value for force. So the SI unit for force, as we know, is Newton. So I'm going to write, instead of F, I'm going to write Newton. And this is equals to, now we have to find capital G. We'll keep it like it is. We'll keep it the way it is. SI unit for mass is kgs, so this is kg. SI unit for mass 2 is also kg, so that is into kg. And the SI unit for distance is meter, so this is meter here. And remember, the distance square is in the denominator, so this has to be squared as well. So now what happens is that we have to move everything from the right hand side to the left hand side in order to find the SI unit for capital G. So here I get Newton meter square divided by kg square in the denominator on the left hand side, and this value is equals to capital G. Now if I move kg square to the numerator, capital G becomes Newton meter square and kg to the power minus 2. So this is my SI unit for the universal constant of gravitation, and therefore here the SI unit turns out to be Newton meter square kg to the power minus 2. Now all of you need to remember this particular value. Capital G is equals to 6.67 into 10 to the power minus 11 Newton meter square to kg to the power minus 2, because this particular value is going to be useful in the numericals which we are going to solve in the future. Now back to our topic. Now here we have the calculated value comes out to be 6.67 into 10 to the power minus 11 Newton meter square kg to the power minus 2. Now there is one thing that is important that we need to note, is that the center of a mass of an object is a point at which the total mass is assumed to be concentrated. Now as this definition is quite hard, I'm going to explain this with a diagram. So let's imagine a ball. So for our convenience, what we do is that we assume that this ball has some mass assigned to it. So let's say this ball has a mass of 100 kgs. Now we all know that this ball is equally distributed with the material inside of it. But what we do for our convenience is that we assume that the mass is located at this particular center, and we can call this center as O, and all of this 100 kg value is at this center O. So what this does is that this eliminates some kind of calculations for us which you are not ready to understand yet. So don't focus on that. What we have to just understand is that any mass for any object is assumed to be at the center of the object. So now this is a sphere. So if I take the case of a square, again the mass will be at center. If I take the case of a rectangle, the mass will be going to be at the center, and so on. If you take a trapezium, the mass will be at the center of the trapezium, it will be somewhere here. If you take a pentagon, again the mass will be somewhere here. So you all get the point, is that the mass that is allotted to the object is assumed to be at the center of the object. Now moving on to our next slide. Now the one thing that we need to understand before we move on to the numericals is that, did Newton derive this exact formula, or was it just luck, just sitting under a tree, just an apple falling, and the apple fell and he found out some numbers just because the apple fell on his head? So we need to go into detail to understand how Newton got this particular formula for Newton's law for the law of gravitation rather. So what we know up until now is that any object that is moving in a circular motion has a constant centripetal force acting on it. So here we have a diagram. So I have an object here, it is moving in circles, and as we know, if this is my center, there is a force acting towards the center. Now if m is the mass, v is the speed, and r is the radius, then the force, that is the centripetal force which is acting on the object, is equals to mass into velocity square divided by the radius of the circle in which it is rotating. So this value is m, this distance is r, and the velocity with which it is moving is v. So therefore, this force that is acting at the center, I'll represent this with red. This force acting at the center is represented by F is equals to mass to velocity square divided by radius. Now, I know this formula is quite hard for all of you to understand, that how did we get this formula, but we don't need to focus on this now. We are going to learn this later on. All we need to focus focus right now is that force is equals to, or rather I should say, centripetal force. Centripetal force is equals to mv square divided by r. Now all of us know that v, or rather distance, is equals to velocity into time. So I can say that velocity is equals to distance divided by time. Now as we can observe that the object is traveling in a circle. So the object is traveling in a circle. So if this is my circle and this is my radius r, my object is going to go, if it starts from here, it will go from here and it will come here. So this one full rotation is the perimeter of the circle. So the distance that it travels is going to be 2 pi to capital R. Obviously we are assuming that the radius here is r. So I can say that v is equals to 2 pi capital R, and here small t is the time it takes to revolve in the circle. So that we are going to denote by capital T. Now what we are going to do this is we are going to replace v in the formula F is equals to mv square divided by capital R. We are going to replace v as 2 pi r divided by capital T. So let's go on further and see what happens. We have F is equals to mass into 2 pi capital R divided by T. Now this is squared. We have to keep everything in mind, and that is divided by capital R. If we solve this, we get m into 2 square is 4, pi square is pi square, and r square is r square divided by t square divided by r. Now if we further solve, so now further solving this, we get f is equals to 4 m pi square divided by t square into r square. Now one of the r will get cancelled, so this gives us f is equals to 4 m pi square divided by, or instead we are going to write it this way, r divided by t square. Now how are we going to relate this to Kepler's law, or how this law relates to Kepler's law? So as we know that in Kepler's law we have square of its period of revolution, that means t square is directly proportional to the cube of the mean distance of a planet. So that means we need a value t square and we need a value r cube. Now here we already have a value t square. Now we don't have a value cube here. So what we are going to do is that we're going to multiply this particular term on the right hand side with r square, and we're going to also divide that same side with r square so that we do not change the equation. So f is equals to 4 pi square m into r divided by t square into r square divided by r square. So this way I did not change my equation, and now I'm going to get some value that is going to be related to the Kepler's law. So I have f is equals to 4 pi square m r cube divided by t square into 1 divided by r square. Now we all have learned in the previous section that t square divided by r cube is equals to k, which implies r cube divided by t square is equals to 1 by k. So now we are going to replace this in our equation. We get f is equals to 4 pi square m into 1 by k into 1 by r square. So this gives us f is equals to 4 pi square m divided by k into 1 by r square. Now the reason I have written this as it is because As we can observe, 4 is always going to be constant. The value for 4 will never change no matter where you go in the universe. So that means 4 is a constant. Same case for pi. Pi value is 3.142857143. That value does not change wherever you go in the universe. Now coming to the object, to the mass of the object. Now the object, when it rotates, its mass will never change when if it's rotating in a circular motion. That means mass is always going to be constant in the motion or during the motion. And now we are left with the constant, Kepler's constant K, which is also another constant. So that means this particular term that we have here is going to be constant. So this implies F is equals to constant into 1 by r square. Now some of you might be wondering that the object is moving in a circular motion, so the radius is never going to change. But as you all can recall, that the Kepler's first law was that the planets revolve around the sun in an elliptical orbit rather than a circular orbit, and that is why the radius or the mean distance from the sun constantly changes, and that is why the radius in this case is not considered to be constant. So this implies that force is inversely proportional to the square of the distance. So gravitational force is inversely proportional to the square of the mean distance. Now, once we have accomplished this, we'll get back to our slides. We can see that F is equals to 4m pi square divided by kr square, but 4m pi square is a constant as none of these values will change, which implies F is equals to constant into 1 divided by r square, and hence F is inversely proportional to the square of the mean distance. And this is how Newton came to the conclusion that the centripetal force acting on the planet is responsible for its circular motion and must be inversely proportional to the square of the distance between the planet and the sun. Now, gravitational force is what allows matter present in all of the universe to function the way it currently does. Just because we have gravity on Earth is why the magnetic forces on North Pole and South Pole act the way they do. The air current, the water current, whatever that occurs naturally on our Earth happens because of gravitation. And this case is not just for Earth. This applies to every object in the universe which is subjected to gravity. Anything that happens is related to gravity. And even though gravity is not one of the strongest forces in our nature, and yet it is an extremely crucial factor in deciding the universe, in deciding the fate of our universe, as all of our universe comprises of massive planets, stars, and other matter which have some kind of mass with them. That's all for this section. I hope this section was easy for all of you to understand. In the next section, we'll be starting off with some numericals, and we'll be moving on to the remaining topics of our chapter from gravitation. Thank you.